Welcome to the second lesson for Area of Study 3. Today we'll be having a look at circular motion. I'm Noah Bajeo and look forward to having you for this lesson. So, what are we going to do? Well, we're going to have a look at, what is circular motion? And then we're going to have a look at all its applications. We're going to look in the horizontal plane, we're going to look in the vertical plane, and we're also going to look at banked tracks. Right, the basics of circular motion. It's important that you understand this because it's going to be the basis for, the entire lesson. So I'll go through it and we'll do it slowly just to make sure that you understand. So, an object travels in a circle when it experiences a net force towards the center of the object of constant magnitude and it's perpendicular to its velocity vector. So it's got to be constant magnitude and it's got to be perpendicular to velocity. Those two things are absolutely crucial, and it's often asked as to what the conditions for circular motion are. So in this case, in our diagram on the left here, we've got the dotted red line representing the net force, which is the result of the centripetal acceleration multiplied by the mass of the green ball. And that comes from Newton's second law. So sum of the forces is mass times acceleration. The blue arrow represents the direction of motion the ball is travelling in at that point of time. And so the eventual path will be that outer purple circle in an anti-clockwise direction. But where does this force come from? Well, in this case, we have that black centre and the black rod applying a tension force to the ball, which keeps it a constant distance away from the centre. But it has a changing direction in terms of that tension force. So the force is applied on the ball towards the centre, and it's perpendicular to its velocity, and it's of equal magnitude. And therefore, you get uniform circular motion. Right, formulas for circular motion. So there's a few handy formulas here. Some are not on the formula sheet that you'll get in your exam, but they're pretty important that you know because they are the basis of circular motion, and circular motion tends to take up a significant part of the end of year exam. So we have the symbols, letters, I guess, representing, so V represents velocity, which is a vector, and it's measured in meters per second. We've got radius, which is R, which is scalar quantity, that's measured in meters. We've got capital T, which represents the period of rotation. In seconds, that's a scalar. F, which represents the frequency of rotation, which is how many rotations per second. So that's measured in hertz or the inverse of seconds. We've got A, which represents, in this case, centripetal acceleration, which is a vector, and it's measured in meters per second squared. And we also have centripetal force, so FC, in newtons, that's also a vector, and M, which represents the mass in kilograms. If you'd like a derivation of any of those formulas, please don't hesitate to contact me via the Airlearners website. The other thing that you should note is that the centripetal force is not a contact force, but it's rather the net force. So it's the sum of all forces, hence the little sum over here. As a basics, generally speaking, to get this result, you just substitute in the V here into this equation over here. So it's pretty straightforward, but if you want any more detail, you're more than welcome to let me know. All right, practice question 1. List the conditions required for an object to move in uniform circular motion. 2 marks, you've got 2 minutes. And you can pause the video and come back when it's done. All right, now that you've had an opportunity to do that question, let's have a look at the solution. So 2 conditions are, the first one is that the net force must act towards the center of the circle, which is known as the centripetal force, and it must have constant magnitude. And the second condition is that the velocity must be perpendicular to that acceleration. Well, now into the content. Horizontal circular motion. So this is where we think about things going around in a circle when there's no change in height above the ground or something like that. So we've got a car going around a roundabout, so that way it's not changing in the horizontal in the vertical plane, and we've got a ball swinging around a pole when it's not changing up and down as well. So those are the kind of two examples. There are lots more, but I don't know, for instance, a Malteser running around the inside of a plate. So there are lots of options. Practice question 2. Consider a vehicle of mass 1,200 kilograms traveling uniformly in a circular path of diameter 10 meters. A. Initially, the vehicle travels at 2 meters per second. Calculate the magnitude of the centripetal force acting on the vehicle as it turns. For 2 marks. You've got 2 minutes, and you can pause the video and come back to it when you're ready. All right, now that you've had an opportunity to do that question, let's go through the solution. The first thing that I would note is the values that are going to be important. So we have over here, we've got mass of 1,200 kilograms. We've got a diameter of 10 meters. It travels at 2 meters per second. So those are the things that we're going to find useful when we've had our formulas. So as you'll see, used from the a few slides back, we've got this formula. The centripetal force is the mass times its velocity squared divided by the radius. And we have all those values, so we can just substitute it in. So what we're going to do, 1,200 multiplied by 2 squared divided by 5, and it's 960 newtons. Now note that it's just asking for the magnitude, so we don't have to give a direction, but if you were, it would be, for instance, towards the center. So the 4 tyres can handle a maximum of 1,500 newtons of sideways friction force on the road. Calculate the maximum speed that the vehicle can travel along the path of diameter 10 meters for 2 marks. So you've got 2 minutes to do this question. It's a little bit trickier than the previous question, but I think you'll be able to do it. All right, so now that you've had a chance to do that question, let's have a look to see how I do it. So from this, I'm interpreting that the total is going to be 1,500 newtons rather than 1,500 newtons per tyre. So we're going to assume that the centripetal force is going to be 1,500 newtons. That's important because that means that we'll be able to use a formula that we also used in the previous question to calculate the maximum velocity. So let's just do that. Let's substitute those values in. 1,200 is the mass from the previous question, and the radius, not the diameter, the radius is 5 meters. And then we're going to solve for the velocity. So we get v squared is 6.25, and then we get v is 2.5 meters per second. Now it said speed, so we don't have to give a direction. So that would be the maximum speed that it can travel. All right, vertical circular motion. This is the second part of 3 parts to this presentation. So roller coasters are a good example of vertical circular motion. It's probably the most classical in that way, because there are 3 options. We can either be going over humps, which is this bit here. It can be going through dips, which is there, and it can be going upside down, which is there. So those are the kind of 3 options for vertical circular motion, and they all have different things that's attached to them. And one of those things is the normal reaction force, and this is a pretty important part. It's a little bit confusing, but again, we'll go through it slowly and hopefully you'll be able to understand. So for each of the situations, the over humps, through dips and upside down, it's really important to understand how the normal reaction force is related to the motion of the body. So over humps. Going over humps, the normal force on the track, of the track on the cart must be less than the gravitational force. So we've got Fg is more than or equal to Fn. And what that means is that the centripetal force, which you can see down here, which is the dotted line, so it's the net force, in other words, the addition of Fg and Fn, means that in terms of its magnitude, it's Fg minus Fn. So note that these are the magnitude symbol, or the absolute value. That means that it's just the value rather than a positive or negative, which would happen if you're adding vectors. So it's just going to be Fc, or the centripetal force is going to be the gravitational force less the normal reaction force. And so that gives you this result over here, assuming that no other forces are acting on the body, so that the normal force you can calculate given all of those values, so the mass, the velocity, and the radius. Through dips, it's the second of the three. So going through dips, the normal force of the track on the cart must be greater than the gravitational force, such that Fn is greater than or equal to Fg. So we've got centripetal force is still going to be the addition of the two vectors, but in this case, you'll see that Fn is a lot longer than Fg. So it's just going to be the magnitude of this one less the magnitude of this one, which is what we've got over here. So it might be quite useful. So as opposed to the previous one, where it's mg minus Fn, this one is Fn minus mg. So that's kind of the distinction between over humps and through dips, which means you get this result. The only thing that's different in this is that it's plus instead of minus compared to the last one, which we can see here. All right, the normal reaction force, but for upside down travel. To travel continuously upside down, contact must exist at the top of the loop. That means that Fn must be more than 0. And because it's upside down, all the forces are acting in the same direction. So we've got Fg is downwards, Fn is also downwards, which means that Fc is going to be the addition of the two magnitudes. But because they're acting in the same direction, we can just write it as Fn plus Fg. You can rewrite that. So for the minimum speed, Fn equals to 0, which leads to this result. So we've got Fc is the sum of the normal force and the gravitational force. So let's just say that Fn is 0. So then you get this relationship. Yeah, Fc equals to Fg. And with this, we can get a nice little formula, which you can see the derivation for in the result here of F equals to the root of Rg or Gr, same thing. So that can be quite useful for finding the minimum speed in a loop, and it often comes up in questions in SACs and exams. So Mark is in a cart of mass 100 kilograms in total, traveling through a loop-the-loop as part of a ride at the local theme park at 15 meters per second. The loop has a radius of 20 meters, and Mark comments that he felt a small force on the track of the track on the cart at the top of the loop. With the aid of relevant calculations, explain why Mark and the cart could still go slower than 15 meters per second and make it around the loop. 4 marks, so you've got 4 minutes. Make sure that you answer the full part of the question, so with calculations and the explanation. And once you've finished, you can come back. All right, now that you've had an opportunity to do that question, let's see what I would do. Well, the first thing is to draw a free body diagram. So that's what I've done over here. I've labelled all my forces, including the net force, and we can see it's probably going to be a little bit helpful in calculating what we need to calculate. So the minimum speed, which is what we want, occurs when the normal force is 0. So if it is 0, then the centripetal acceleration is equal to the gravitational acceleration. And so then we get this formula, which we saw on the slide before, and so V is going to be 14 meters per second. Now the important part, to link it back to the situation, is that because the minimum speed that Mark and the cart can go at is less than 15 meters per second, it's 14 meters per second, they would still be able to complete that ride at a slower speed. All right, practice question 4. Jane is building a ball luge in her backyard. To operate correctly, a ball of mass 100 grams must travel through a quarter circle dip of radius 50 centimeters in no more than 0.20 seconds, so that it will reach the end of the luge track. Calculate the minimum magnitude of centripetal force experienced by the ball as it moves through the bottom of the track. Now, this is 3 marks. Make sure that you read that question carefully. You can pause the video and come back when you're ready. All right, now that you've had a go at that question, let's see what I would do. I would use this formula for starters, because what we have here is we've got something to do with time. So that could be important. We've got the radius, we've got the mass, but we also have a really important piece of information here, which is that it's a quarter of a circle. Now, a lot of people will miss that and assume it's the full circle, So that needs to be accounted for. Because t represents, in this equation over here, the period for a full rotation of a circle, then t has to be 0.2 multiplied by 4, which is 0.80. And so then we have to substitute in all of our values. So we get 4 pi squared multiplied by 0.1 multiplied by 0.5 divided by 0.8 squared. And what we get is roughly 3.08 newtons. And again, because it's magnitude, you do not need to state a direction. So that would be the minimum magnitude of centripetal force, because it can go through in less than 0.2 seconds. If it is less than 0.2 seconds, then FC will increase. Okay, banked tracks. A banked track is quite literally a track or a road or a path, whatever you want to call it, that's inclined on an angle perpendicular to the direction of motion. So what I mean by that is that this vehicle here, this truck, whatever you want to call it, will be traveling in that direction around the embankment, and we'll have this angle over here that we can call theta. The bank track is a common application of circular motion in the horizontal field. So it's a really good way of kind of testing your knowledge with some more practical questions. So in terms of forces on a bank track, this is kind of how it works. We have the vehicle and we have its gravitational force or weight that goes down there, and that must be counted equally by another force that acts somewhat in this direction, straight up, which is coincidentally going to be the normal force, and it's going to have the same height along here, this length from here down to here. That force has to be the same as that force here. So what ends up happening, and because the normal force has to be a 90-degree angle over here, maybe it'll be easier if I just show you here. So that is going to be a 90-degree angle, and that way there's going to be a component of the force that acts in that direction, and that is exactly what this force, this net force, is over here. So that's what you're going to get in terms of your horizontal circular motion, which is why that's the centripetal net force acting towards the center of that circle, and that's pretty much how it works. So formula, they look complicated, but they really aren't. The x's and y's are all to do with the direction that they're acting in. So that's part of that key there. So the rest is pretty simple. So we've got the normal reaction force is in the vertical direction is the same as the magnitude of the gravitational force, so it's equal to mg. And because we know that, we can then do this. So the in the x direction, the normal reaction force is going to be the y component multiplied by tan theta. So it's going to be mg tan theta. And if there's no sideways contact force or friction or anything like that, which usually is the case in physics, in fact, I can't really think of a time when it hasn't been, then we can say that the centripetal force is the same as this force here, or this force, which is the same. So what ends up happening is we get mv squared on r equals to mg tan theta. The m's cancel, which you can see here, there's no m here and there's also no m here. So you get v squared on r equals to g tan theta. And so with that, we can rearrange it much in the similar way that we did to the v equals to the square root of rg or gr earlier on. We can get the same kind of situation, and that will also give us a minimum speed. With that, we also have the acceleration, if you ever require it, of g tan theta. Okay, question 5. This is quite a decently length question, so strap in. John is driving around a banked track of radius 100 meters, which is sloped at an angle of 15 degrees from the horizontal. Calculate the speed that John is traveling at, given that there is no sideways frictional force. Give a relevant unit. All right, so you've got 3 marks, so 3 minutes. You can have a go at that and get back when you're ready. All right, so now that you've had a go at doing question 5a, let's see what I'd do. So the first thing is I would draw a free body diagram in FBD. It's a little bit more of a fancier vehicle than in the previous question, but you'll notice here that I've put in the 15 degrees, and I'm actually going to underline this over here. So we're going to have a radius of 100 meters. That can be quite important. So we want the speed, and we can use the formula that we had previously, but we're also going to, because it's 3 marks, give a bit of reasoning as to how we got to that formula in the previous slide. So we're going to say this, and it would be a good idea also to have your X's and Y's now, just so that the assessor knows exactly what you're talking about when you're talking about X's and Y's. So this is what I would do. I would set this out as follows. I'd give this, I guess, derivation of the formula, and then I'd directly just go in and substitute the values. So that's what I've done here. I've substituted G for 9.8, which is the same thing. Given the angle, which is 15 degrees. I've given the radius here, which is 100 meters, and that way I can solve for V, the velocity, which is what I'm about to do here. And you'll get 16 meters per second. It's not quite exactly 16, it's about 16.2, I believe. But it is important to know that the minimum number of significant figures here is 2. So 15 degrees is 2 significant figures. So the most number of significant figures that we can give is 2. So that's why it's 16 meters per second. And that's the result that you should continue to use. All right, here's a biggie. Question 5b. While the speed limit on the road that John's traveling on is 80 kilometers an hour, there's a recommended turning speed of 60 kilometers an hour around this section of the track. So explain using the terms friction, normal reaction force, and centripetal acceleration why this is the case. It's 3 marks. It's an explanation question, so it may take 4 or so minutes. So you can have a go at that. It may take you a little while, but come back when you're done. All right, now that you've had an opportunity to do that question, let's have a look to see what I do. Now, the first thing is, with these explanation questions, they're not always so easy to mark, but because there's 3 marks, you're going to say, well, there's at least 2 for mentioning all 3 of these things, and then 1 mark for explaining why this decision has been made to give the recommended turning speed. So this is what I've written. As John travels around the track, he's required to steer the vehicle directly ahead at roughly 16 meters per second, which is just less than 60 kilometers. It's about 57, 58. This is due to a component of the normal reaction force, so you have linked that term there, as a result of the angle of embankment acting perpendicular to the direction of motion, stipulating circular motion. So there's a couple of things I've done with that sentence. I've shown my knowledge of what bank tracks is and talked about the angle, how that normal reaction force comes about. I've given what the conditions are for circular motion, which is acting perpendicular to the direction of the motion. And because it's traveling at the same speed, it's obviously going to be the same acceleration. So as the vehicle experiences centripetal acceleration, so I've used that term again, as the vehicle experiences centripetal acceleration through the circular path, a velocity greater than 60 kilometers an hour will result in the necessity to turn the wheel to provide an additional frictional force to remain on the road. Hence, for a more efficient, comfortable and safe journey, the recommended speed around this section of road is 60 kilometers an hour. So there's a few bits here. I've decided to put in that friction force as required, and I've also mentioned some reasons. So it's more efficient because they've got to do less steering. It's more comfortable because they don't have to steer hard. This is kind of the natural path to follow around the curve, and it's safer because if they went faster, what would end up happening is they get higher and higher up and possibly cross over into the next lane. So that's why I've written those things down there, and that's an answer that would get full marks. Okay, well, we have completed the lesson. Now we'll just review what we've done. We've gone through circular motion in the horizontal plane and the vertical plane, and we've also had a look at banked tracks. We've applied all the theory that we've learnt, all the formulas, with 5 practice questions, which is quite a lot, but it's good to be able to practice what you've learned to make sure that you've understood it. In our next lesson, we'll have a look at projectile motion, including horizontal, vertical, and oblique motion. And that's quite a big lesson, quite important, also a pretty solid part of area of study 3, and also comes up quite a lot in the exam. So thanks for your attention. Hope that you found this lesson interesting, that you learned something new. If you'd like to get in touch with me, have any questions, any queries, or just some feedback, feel free to go to airlearners.com, and you can find me on the tutors page. You can search my name up. It's there. So thank you very much. See you next time.